Hello everybody, I am Tommaso Pardi and I am a PhD student, part of the Extreme Robotic Lab at the University of Birmingham. In this work, we present a path planner that maximizes the manipulability throughout the path, which is of particular interest in forceful operations like the cutting for nuclear decommissioning. This work has been accepted to RAL and presented at ICRA 2020. The nuclear decommissioning is a challenging task that the community must face for the next centuries. Nowadays, most of the operations is performed by human operations that risk their health entering radioactive cells for dismantling purposes. Since the 70s, all the decommissioned nuclear wastes have been stored using barrels like the one in the picture, that today lack of records and risk to crack open. We then need to cut them open and segregate their content to have more efficient and cost-effective maintaining of such long-lasting wastes. Because of the risk for the human to operate in such scenarios, we must deploy robotic solutions. Therefore, we studied how the expert human operators perform the task of cutting barrels using teleoperated hydraulic arms and scissors. The rudimental teleoperation system does not help to operate in any way, and the technicians most of the times make a rough cut along a straight line. Although it is natural for human beings, a robot may lack of the robustness to do a straight line because of its kinematics. So we propose to plan a path incorporating kinematic robustness, which would make the robot able to perform the process autonomously. Many possibilities to introduce the concept of robustness within the framework of the path planning exists. Here, we leverage on the manipulability to embed information of the remaining available Cartesian movements for a robotic arm in a certain configuration. If we take a robot arm and we constrain the norm of the vector describing its configuration's velocities to be unitary, we obtain a map that connects the vector of configuration's velocities, q dot, with the end effector Cartesian velocities, r dot. This matrix is usually called manipulability matrix, and here we denote it with the capital M. Taking the singular value decomposition of M, we obtain the standard matrices U, sigma, and V, where sigma contains the eigenvalues of M, and U is composed of the relative eigenvectors. Thanks to the properties of the manipulability matrix, we can shape M as an ellipsoid whose dimension depend on the size r, which is the vector of generalized coordinates in Cartesian space. In the picture, we report the so-called manipulability ellipsoid for the only positional elements in R. The vector u1, u2, and u3 show how much capability of making a movement is left to the robot send effector along each direction. In order to avoid the use of the full manipulability matrix, many metrics have been proposed to shrink the information into a single number. One of the most common is the Yoshikawa manipulability metric, which takes the square root of the eigenvalues of the matrix M. By definition, W depends on the robot configuration and it is proportional to the volume of the ellipsoid. Therefore, a low value of W results in low manipulability values, and high values means greater manipulability. Here, we are interested in using the Yoshikawa's manipulability metric not to only assess a configuration, but to find the sequence of configurations that drives the robot's end effector from a starting point to a destination point while continuously touches the object surface, and yields maximum manipulability throughout the entire path. Thanks to this designing, the resulting path will allow the robot to overcome possible uncertainties or model errors that are not easy to predict beforehand. We then design an objective function which sum up all the manipulability contributions along a sequence. Looking at the proposed metric, we notice that it has two major properties. It uses the inverse of the Yoshikawa's function and it is written in an iterative fashion, where q nu is the I plus 1 element of the sequence. The former property accounts for the requirement of minimizing the objective function rather than maximizing it, while the latter helps to deploy the cost in iterative algorithms. A second demand of many forceful operations, such as the cutting, is to stay in contact with the object throughout the task. However, we have little information about the scenario that we are moving in, and the sensor readings are full of noise because of the radiation intensity. We therefore must make some assumption on the objects we are going to interact with, and we assume that the object surface, or at least the portion of surface that we want to operate with, is a Riemannian manifold. A Riemannian manifold is a n topological space equipped with an inner product G on the tangent space of every point P inside the manifold, which changes smoothly from point to point. Taking any point onto the manifold, we can approximate the neighborhood of this point with a tangential plane. We usually call it TPM. Thanks to the Riemannian geometry, two maps exist that brings points from TPM to M and vice versa. Those functions are called exponential map and logarithmic map, respectively. Let's make an example to understand how we want to exploit this assumption. Given a sphere in red, we perceive a noisy representation of its shape by a point cloud, black points around the sphere. Taking a point onto the manifold, P nearest, let's compute the tangent plane to P nearest using the information in the point cloud. Although the data might be noisy, the Riemannian assumption guarantees the object to be smooth, and the algorithm, like PCA, can fit the right plane with great accuracy. Then, we sample a point from the point cloud, P rand, and we project it to TPM. We call it PT. Now that we have a point on the tangential plane of P nearest, we would like to use the exponential map to bring it on the real manifold. However, the points P nearest and PT might be extremely far, and the generated point might violate the Riemannian assumptions. Therefore, we take a step toward the direction of PT, starting from P nearest. The new point, PT beta, is still on the tangent plane, and it is as close as we want to the starting point. So we apply the exponential map, which provides a new point P nu on the manifold in red. We care to notice how, by construction, this new point is on the real sphere and it is not part of the points in the point cloud. Our approach for maximizing the manipulability along a path and constrain the end effector to stay in touch with a surface is algorithmic agnostic, and it may be used for every iterative path planner. However, we decided to integrate the proposed approach with one of the most common path planners in the robotics community, the RRT star. The novel algorithm is called RRT star RMM, where RMM stands for Riemannian Mapping Manipulability. Let's break down the algorithm and see how it works. At first, we fed the algorithm with the point cloud and the initial and goal points, and we initialize the tree to the starting point. Then, we select the maximum number of iterations that we want our algorithm to iterate for. At each iteration, we obtain a new point from the point cloud, and we apply the Riemannian manifold procedure that I explained before to generate a new point P on the object surface. Then, we check whether the new configuration is collision-free or not. If yes, we compute an objective function, which is a linear combination of our manipulability cost and the distance cost, typically of the RRT star. Then, we assess whether the new point might improve the nodes already present in the tree and reroute the tree. We made an extensive set of experiments over a variety of different object shapes, and here you see 4 objects: a curved surface, a helmet, a cylindric barrel, and a flat object. In all the experiments, we assume the robot base to be mounted on a pillar by the table. Our algorithm takes the point cloud displayed next to the experimental setup and the initial and goal points by their Ruko markers. Hence, it proposes a path with high manipulability to connect the 2 points. We notice how the algorithm usually selects paths that are departure from the shortest path. Although the manipulability depends on the robot kinematic, our algorithm works with URDFs and it can be easily deployed on different arms. Here we tested our approach on a simulated Sawyer and a real Panda robot. You can see how the RRT star RMM consistently obtains configurations with higher manipulability than a standard RRT star. Taking a closer look at the results, we see how the RRT star RMM consistently perform better than the naive RRT star. Although the comparison seems unfair, it is what we can expect in teleoperation tasks. The only object where the proposed approach does not improve the manipulability with respect to the RRT star is the barrel. We believe the object's point cloud was too small and the possible paths were limited, and it resulted in the RRT star RMM behave like the RRT star. As for the length of the path, the RRT star obtains shortest paths as we expected. The only noticeable outlier is the odd variance in the path length for the curved object in the RRT star RMM. We reckon the initial positions we selected in the experiments were particularly low in manipulability, and the algorithm found many possible paths to connect the two points. Thank you.